Here we're going to talk about intermolecular forces. So some of the intermolecular forces we'll talk about are dipole-dipole interactions, hydrogen bonding, dispersion forces, sometimes called London dispersion forces, and then lastly ion-dipole interactions. So intermolecular forces, they're attractive forces that hold particles together in the condensed phase. So meaning they just have to be close to each other. These molecules have to be close to each other. The magnitude of these intermolecular forces is what determines whether the particle is made up of a gas, liquid, or solid at a particular temperature. Attractive forces act between atoms or molecules in a pure substance. Are the following interactions. They're called van der Waals forces. So dipole-dipole interactions, hydrogen bonding, ion dipole, and dispersion forces. And they all have varying strengths, and this can help dictate whether something's going to be held tightly together, like as in a solid, or very loosely together, as in a gas. So first, talk about dipole-dipole interactions. These are the attractive forces that act between polar molecules. So we're already familiar with how to determine whether something is polar or nonpolar. So this requires that the molecule be polar. So here we have HCl, and hydrogen is partially positively charged. The chlorine is more electronegative, so it's partially negatively charged. That is a polar covalent bond. And you can see just fairly vaguely the positive and negative ends of that molecule can line up next to each other in a solid phase, for example, or even in a liquid phase. In general, those positive and negative, partially positive and partially negative ends will line up near each other. So here's some examples of some molecules and their structural formula. Here we're quantifying their dipole moment, so talking about how polar or nonpolar they are. So propane is very nonpolar, and you can see it has a very, very low boiling point. It's not being held together very strongly at all, where if you go up to acetonitrile has the highest dipole moment here. So it has the highest boiling point. It is the most polar molecule, so it's going to be held together, let's say in that liquid, it's going to be held together much more strongly. So it's going to be, you're going to require adding more energy in order to break those intermolecular forces apart to get it into the gas phase. So that's why it has the highest boiling point, which still isn't very high. It's 82 degrees Celsius. So hydrogen bonding, it's kind of unfortunate that it is called hydrogen bonding because it is not a chemical bond. These are all intermolecular forces. It is really just a special type of dipole-dipole interaction. It is a very strong dipole-dipole interaction, and that's why vaguely it's more been called bonding for historical reasons, even though, again, it is not a chemical bond. So this occurs when a molecule has a hydrogen bonded to a small, highly electronegative atom, and the three examples that you need to know are nitrogen, oxygen, or fluorine. So, for example, this is HF. So you have fluorine and hydrogen there. Hydrogen is partially positive, fluorine partially negative, and that's because fluorine is the most electronegative atom. And you can see again those dotted lines are representing that hydrogen bond, that intermolecular force that's holding adjacent HF molecules together. So they're going to line up in a very ordered way because of that. And actually, based on that, there's a particular, because of these highly electronegative atoms, there's a general trend on periodic table with the period. You can see where things like H2O and HF and NH3 all have very high, in general, high boiling points. In comparison to some other simple molecules that are still very small. So yeah, here you can see those three. Those all have hydrogen bonding interactions, where a lot of these have dipole-dipole interactions, but that you can see they're weaker. That's why they have lower boiling points, for example. And methane, very, very low boiling point, because that's nonpolar. That doesn't even have dipole-dipole interactions. Yeah, it's very low boiling point. So at room temperature, methane is a gas, where that is not true for water, of course. All right, so London dispersion forces. This actually, all molecules have this. It is kind of the simplest force. The only reason we didn't talk about it first was because we needed to know something about dipole, and really this is can be in any molecule, like I said. That is includes polar or nonpolar molecules. So nonpolar molecules, this is the only thing, the only force that a nonpolar molecule will have in terms of intermolecular forces. And this is similar to a dipole-dipole, but weaker in the sense that it is an instantaneous dipole. So electrons in a molecule have some freedom to move about, and at any given point in time, the molecule may have a non-uniform distribution of electron density. So it means a bunch of the electrons may be on one side of the molecule versus the other temporarily, which will form an instantaneous dipole. So that's what you're seeing here, where you kind of have a partial negative on one side of the molecule and a partial positive on the other side, even though it's a nonpolar molecule as a whole. So that instantaneous dipole in one molecule can induce dipoles in neighboring molecules. So you started with this kind of instantaneous dipole, and it will induce a dipole in another adjacent molecule. So since this was partially positive, it's going to pull some electrons on this molecule towards it, making that partially negative. So you're going to form these little instantaneous dipoles like this, even though most of the molecules are nonpolar. So it looks, this little setup right here looks very similar to dipole-dipole interactions, but it's a very weak dipole because it's an instantaneous dipole. So the magnitude of the dispersion forces depends on how easily the molecule's electrons can be polarized, meaning how easily can you create that instantaneous dipole. And really, polarizability of a molecule increases with the increasing number of electrons. So it tends to be large atoms or molecules with large amounts of electrons will have slightly stronger dispersion forces. The next intermolecular force is ion-dipole interactions. These are Coulombic attractions between ions, either positively or negative, and polar molecules. So Coulombic attraction, that's the electrostatic potential between an ion and a polar molecule. So similarly to how we know a positively and a negatively charged ion will have Coulombic attraction, that is stronger even than an ion-dipole interaction. That's an ionic bond, right? So that comes into ionic bonding territory. This is still an intermolecular force. This isn't a chemical bond, but this is between an ion and a kind of a partial ion, meaning a polar molecule, something that has a dipole associated with it. So this is what something like this might look like. So the magnitude of the ion-dipole interaction depends on the charge and the size of the ion, and the dipole moment and the size of the polar molecule. So for example, here we have water, which we know is a polar molecule, and two different cations. So here we're lining up the negative portion, the negative side of the water with the positive cation. And sodium is much larger than magnesium 2+, and it only has a +1 charge. So it's a relatively weak interaction. Well, ion-dipole interactions are much stronger even than dipole-dipole or hydrogen bonding or any of those. So it is a very strong interaction in general. But sodium with water, it will be a weaker interaction than magnesium 2+ and water, which is a strong interaction since it is smaller and more heavily charged, right? So this is very similar to when we talked about lattice energy in terms of ionic compounds, where magnitude of charges mattered for Coulombic attraction, and the size of those also to a minor extent mattered. So molecules can also exert repulsive forces on one another. There are repulsions between electrons and between nuclei in the molecule can become significant. And this is based on the distance. So the magnitude of these repulsive forces rises very steeply as the distance separating the molecules in the condensed phase decreases. So as you get really, really close, you're going to have a lot more repulsive forces. And this is a really important feature because this is the primary reason why liquids and solids are so hard to compress. So liquids to a very small amount can compress, solids even smaller. So you really have a very significant amount of repulsion between those electrons and the two nuclei, for example, when you try and get too close. So there's a kind of an ideal distance, and that's what gives you some of these properties like the density of a liquid or a solid. So here are all of the types of intermolecular forces. Once again, this is now in order of their relative strength. So London dispersion forces are the lowest in terms of their strength. You can see there's a little asterisk there that saying that the dispersion force can become very strong and as strong and even stronger as other for molecules with high molar mass. So since this is kind of a cumulative intermolecular force, it can compound. It can add up. Any little the individual force is very small, but if it has a very, very long molecule, they can become actually very significant. So, and this is for all molecules or atoms. And again, that was that induced dipole interaction. And then we have a little bit stronger. You have dipole-dipole. This required polar molecules. Then a special type of dipole-dipole, which was a very, very strong dipole-dipole, which was called hydrogen bonding. And this is where a molecule containing hydrogen is bonded to fluorine, oxygen, or nitrogen. Since fluorine, oxygen, and nitrogen are very, very small and very electronegative atoms, you get this particularly strong dipole that is occurring. And this is water being the prime example of hydrogen bonding. It is a very small and light molecule, but it actually has a very high boiling point because of these very, very strong intermolecular interactions. And then lastly, you have ion dipole, which is even stronger. And there you have a full positive charge with a polar molecule. So a full-blown ion. Or this could also be a negative ion. So for example, when this is like if you dissolve sodium chloride in water, you have sodium that is looks just like this diagram. And you also have chloride, but the waters would be flipped around the other way because the other portion of that dipole would be pointed towards that ion. And these are quite strong. These are still weaker than chemical bonding. So naturally, the next thing on this list could be ion-ion interactions, right? But that again is ionic bonding. And likewise, these are still not as strong as covalent bonding. So if you remember looking at your chart in terms of kilojoules per mole, here we have, even with the strongest interactions, we're maybe getting to 100 kilojoules per mole. And if you remember the bond enthalpies chart from the past, those covalent bonding interactions were often many hundreds of kilojoules per mole. So this is still kind of in an echelon below chemical bonding. And because of this, things like hydrogen bonding or dipole-dipole or even ion dipole, they're constantly breaking those intermolecular forces and reforming them kind of again and again and again, assuming they're in a liquid phase or a gas phase or something like that, where that's not really happening with covalent or ionic bonding, right? Those bonds are being held in place unless you perform a chemical reaction. So let's try some of these problems. So what kinds of intermolecular forces exist in CCl4? Okay, and then these other ones. So first and foremost, you want to draw Lewis dot structures for all of these. So you probably want to pause and do that. And then secondly, we want to look for polar covalent bonds. So if they have pure covalent bonds and that's it, it's nonpolar. So we can stop right there. And know that if it's nonpolar, the only thing that is available is London dispersion forces. Okay. Or we can find that there's polar covalent bonds, and then we would need to see if those cancel out with each other, for example. Remember, something like carbon dioxide, it has two polar covalent bonds. The carbon oxygen is a polar covalent bond, but they were exactly 180 degrees from each other. So they ended up canceling out. So you'd get a nonpolar molecule despite having polar covalent bonds. Okay, so that's something we need to think about. So molecular geometry starts to play a role here, in terms of polar versus nonpolar. And then if we do have polar covalent bonds, is one of those polar covalent bonds the special polar covalent bond that is oxygen hydrogen, nitrogen hydrogen, or fluorine hydrogen? If that's the case, then you have hydrogen bonding. And then lastly, if you're looking for something like an ionic compound that is soluble in water, for example, that would be an example of ion dipole, right? Where you're forming an ion in a polar solution, in a polar solvent. Okay, so this is what these look like. So you have CCl4. It has polar covalent bonds, but they are all 109.5 degrees. That's an sp3 carbon. They're all, and so therefore they cancel. So it's nonpolar. So that only has dispersion forces. All right. This next one has an oxygen-hydrogen bond, so it has hydrogen bonding. And it should be noted that it also, it has everything associated with all of the lower level ones as well. So it has hydrogen bonding and dipole-dipole and London dispersion forces. So the strongest intermolecular force is hydrogen bonding, but those other intermolecular forces are still present and available. Okay. Then the next one, you do have a polar covalent bond there, the C double bond O. It is polar. It is not any special type of polar bond, so there's no nitrogen hydrogen, fluorine hydrogen, or oxygen hydrogen bonds. So it's dipole-dipole is the strongest intermolecular force, but it also has London dispersion, of course. Okay, and then lastly, SH2. SH2 is very similar to H2O in terms of it has the same Lewis dot structure as water, so it is a bent feature or bent geometry. There's no nitrogen, hydrogen, fluorine hydrogen, or oxygen hydrogen. Therefore, it's just dipole-dipole and London dispersion. And that's because these are polar covalent bonds, this sulfur-hydrogen bond, and they are not 180 degrees from each other. If you recall this one is actually like 92 degrees from each other. This is an sp3 sulfur in its geometry.